Alrighty, next what we're going to do is we're going to look at a couple examples or a couple different scenarios in which eigenvalues and eigenvectors are very apparent and kind of at the core of the understanding and solving problems surrounding these applications. So the first one is not really an application, but kind of a more difficult or more foreign example, and that's to consider what happens when your eigenvalues are complex. So let's compute the eigenvalues. So what we want to do is compute the eigenvalues and vectors for A, which is 1, 0, 0, 0, 2, 1, 0, negative 1, 2. All right, so the process is the same. So the process is the same, but the arithmetic sucks when lambda is complex. But at least the process is the same, right? So you know kind of what path you're going on. Well, how do we find eigenvalues? Or how have we found eigenvalues before? Well, we find the roots of the characteristic polynomial, which is the determinant of lambda I minus A equals 0, right? Well, that's the determinant of, we're going to have lambda minus 1, lambda minus 2, lambda minus 2 along the diagonal. And then for everything non-zero, we flip the sign, right? So we have 0, 0, 0, 0. And then we have negative 1, 1. We're finding the determinant of this matrix, which is equal to 0. Well, what's the determinant? The only term that's going to be non-zero is the first term of the determinant, right? Well, if you're choosing either the first row or the first column, and that's going to be lambda minus 1 times lambda minus 2 squared minus negative 1, so plus 1 equals 0, which simplifies to lambda minus 1 times lambda squared minus 4 lambda plus 5 equals 0. And then you can see here the roots are when lambda minus 1 equals 0, which gives us lambda 1 equals 1 from here. The two roots from this quadratic here, well, you would have to use the quadratic formula. And what you get is lambda 2 equals I plus 2, if I remember correctly. And then lambda 3 is 2 minus I. So now, right, finding eigenvalues is no different. It's just you kind of have to use the quadratic formula to figure out what the complex roots are going to be. Now we know how to find eigenvectors for real valued eigenvalues. So I'll leave that as an exercise. And here we'll just say x1, whoops, for lambda 1 equals 1, you get the basic eigenvalue. I believe I got x1 is 1, 0, 0. Okay, now what do we do for lambda 2, which is 2 plus I, right? Again, the process is the same. What you're looking for is the vector. Sorry, that looks like an x, that's a lambda. You're looking for the vector capital X2 such that lambda I minus A times x2 equals 0, right? But we're looking at a complex eigenvalue, so we have 2 plus I times capital I minus A times, and let's write x2 as x sub 1, x sub 2, x sub 3, right? And this is equal to 0, 0, 0. Well, the arithmetic is the same. It's just a little more complicated because you're dealing with complex numbers, right? What you get here, well, you come back to this matrix, plug in lambda equals 2 plus I, and the result is, let's see, what did I get? 1 plus I, 0, 0, 0, I, 1, and 0, negative 1, I. And then the eigenvector x2 consists of components such that this equality holds, right? And what are we doing here? Well, to find x1, x2, x3, we know how to solve a system of equations. We write the corresponding augmented matrix. So we have 1 plus I, 0, 0, 0, 0, I, 1, 0, and then 0, negative 1, I, 0. We need to put this into reduced row echelon form. Well, how do we do that? We have a lot of zeros and we're pretty lucky. The first thing I would do is scale all of the rows so that the diagonal has an entry of 1. So let's say row 1 is replaced by 1 over I plus 1 row 1. Row 2 is replaced by 1 over I, row 2, and then row 3 is replaced by negative 1, row 3. We do all that, we get 1, 0, 0, 0, and then 0, 1, and I want you to verify. Here's, prove this. 1 over I equals negative I. That's an important and very useful relationship, and well, you can prove it pretty easily. Just take, right? How do you get rid of the complex number in the denominator? You multiply the top and bottom by the complex conjugate, which is multiplying the top and bottom by I, which then you get I over negative 1, which is negative I. So there, QED. So 0, 1, negative I, 0, and then 0, 1, negative I, 0. You see row 2 and row 3 are the same. So if you replace row 3 with row 2 minus row 3, what we get, so row 3 is equal to row 3 minus row 2. This gives us 1, 0, 0, 0, 0, 1, negative I, 0, and then 0, 0, 0, 0. Well, then what does this mean? The first row tells us that x1 is 0. The second row tells us that x2 minus ix3 equals 0, and that x3 equals x3. Well, what does this mean for the eigenvectors, right? This is capital X2 now, right? So here, these are the variables or components of X2. Well, this means we have a free variable, let's call it t, and that will be t times 0. And then you add this over, you get that x2 is ix3, so I times t, and then x3 is x3, so you just get 1, right? And so you can conclude that the basic eigenvector, well, let's say, for lambda 2 equals 2 plus I, the corresponding eigenvector was x2, which is 0, I, 1. And so you can see the process is the same here. And you can do the same thing for x3. And if you do that, so here's an assignment, right? Not literally, but show that x3 is equal to 0, negative I, 1. And, you know, that's corresponding to lambda 3 equals, I believe it was 2 minus I, right? So you go through the same process. You plug in lambda 3 to the equation lambda 3I minus A x3 equals 0. You get a system of equations, and then you solve that system of equations by putting the matrix in reduced row echelon form, blah, blah, blah. So you can see the process is the same, but it's important to work through examples. Even though the process is the same, it feels different, right? The arithmetic is very different. When you're putting a matrix in reduced row echelon form and the entries are complex, well, then the arithmetic gets much more complex, right? And so it's important to go through and work through explicit examples, even though it's the same process. Let's do another example of how we can use eigenvalues and eigenvectors to raise a matrix to a higher power rather quickly. So let's let K be a positive integer. So this z greater than or equal to 0, this is the set of n in z such that n is positive, right? So I guess I could just say the natural numbers. That's a little more natural. And then let's say we have a matrix A. This is going to be an n by n diagonalizable matrix. And let's say we want to compute a to the k. Well, how would we do that? First, why do we care, right? Well, one of the reasons we care is because we know we can think about a matrix as representing a linear transformation, right? And in particular, if it's an isomorphism, that's a one-to-one correspondence of changing a basis, right? And maybe you want to do that action an arbitrarily large amount of times, right? Well, then finding out the linear transformation for, say, maybe a rotation or reflection of your Euclidean space, say you want to do that 800 times, right? Well, to find the linear transformation by hand would be a nightmare. But it's less of a nightmare using diagonalizable matrices. So how do we use diagonalizable matrices to compute higher powers of a matrix? Well, I have the following claim. A is diagonalizable means, well, before the claim, let's say A diagonalizable implies there exists a diagonal matrix D such that A is similar to D, which this statement implies that there exists an invertible matrix P such that A is equal to P inverse DP, right? So the claim is that if you take A to the K, then that's the same as P inverse D to the K P. So let's prove this really quickly. Well, what is A to the K? That's K times. But we know A is similar to a diagonal matrix, so we can write A for every product or every factor here. We can write A as P inverse DP, P inverse DP, et cetera, K times, right? And then by the associativity of matrix multiplication, we can regroup here. We can rewrite this pretty lengthy product as P inverse D times P inverse DP. D and then P inverse, et cetera, right? Well, then what happens to this product when you regroup this way? It kind of telescopes, right? All of these P times P inverse, these simplify to the identity, and then the product terminates with DP, where there was like a P inverse just before it. And what are you left with after the simplification? You're left with K copies of the diagonal matrix, and you're also left with the very first and the very last factor, which is P inverse D to the K P. QE. So why does this help us, right? Well, if we say, okay, we want to find some arbitrarily large power of a matrix A, what we've done here by this claim is say, okay, we'll pass that to computing an arbitrarily large power of some other matrix, right? Well, why was that beneficial? If you think about the diagonal matrix, which is, let's say, D11, D22, blah, 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 DNN, zeros everywhere else. Let's look at what happens when you take D squared, right? When you take D squared, you have this times itself, and what you end up getting is D11 squared, D22 squared, blah, 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 DNN squared, which means for a diagonal matrix multiplied by itself k times, well, that's just raising each entry along the diagonal to that power. So this is, in fact, much simpler than literally taking a product of two matrices k amount of times, right? Okay, since we know that, let's do an example. Let's say we want to compute, so let's find a to the 50th power for a is given by 2, 1, 0, 0, 1, 0, -1, -1, 1. Okay. So how do we find a to the 50th, right? Well, we find a to the 50th by utilizing the claim that we've just proven, right? So we know, well, let's say if a is diagonalizable, then a to the 50th is equal to P inverse D to the 50th P, right? But we don't know if it's diagonalizable or not. So what we would have to do first is verify that it's diagonalizable. Well, how would we do that? What we can do is, we've seen an example. So for the sake of time, spoiler, it is a diagonalizable matrix because you compute P, which remember P is x1, x2, x3, which are the eigenvectors of the matrix A. See if that's if the inverse exists. If it does, then the diagonal matrix D is just the eigenvalues as the entries along the diagonal. And so, well, let's write this out algorithmically here. So what's step 1 for computing a high power of a matrix? You need to diagonalize A. Okay, so assuming we go through all the computation, you get that the diagonalization is 1, 1, 2, 0, 0, 0, 0, 0, 0. Cool. Then step 2 is to set up a to the k equals P inverse D to the k P, right? And for us, k equals 50. So let's just say a to the 50th equals P inverse D to the 50th P, right? And so under the assumption that we did the computation to find eigenvalues and eigenvectors, right, you have to do that to figure out what the invertible matrix P is, and then the eigenvalues tell you what D is, right? So assuming we did that, what we would get, or what we will get, is that P is 0, 0, 1, negative 1, 1, 0, and then negative 1, 0, 1. And then you'd have to take the inverse, right? Because what we have to take this product. So we need to find P, D, and then also P inverse. I'll leave the arithmetic for you all to verify. You get that P inverse is 1, 1, 1, 0, 1, 0, negative 1, negative 1, 0, right? So then what is step 2, right? Well, that was kind of step 1.9 or 1.5. We have to set this product up. So a to the 50th is equal to P inverse 1, 1, 1, 0, 1, 0, negative 1, negative 1, 0 times d to the 50th, which was 1, 2, 2, 0, 0, 0, 0, 0, 0. If I'm not mistaken, nope, I am mistaken. And that's to the 50th power times P, 0, negative 1, negative 1, 0, 1, 0, 101, right? Well, we've seen that the product of a diagonal matrix with itself is relatively easy to compute, because what happens is the power is just transferred to the entries along the diagonal, right? And so what we get is that a to the 50th is P inverse again. So 1, 1, 1, right? 0, 1, 0, negative 1, negative 1, 0. And then the diagonal matrix to the 50th power is 1 to the 50th, 1 to the 50th, 2 to the 50th. So I'll kind of group my entries here so that's not confusing. Right, there's the diagonal. And then we were taking that times P, which is 0, negative 1, negative 1, 0, 1, 0, 1, 0, 1. And then you can take the product here, and I would, in the computation that, like when I solved this myself, I just left that as 2 to the 50th power, right? And so what you should get after you take the product of those three matrices, you should get 2 to the 50th, 2 to the 50th minus 1, 0, 0, 1, 0, 1 minus 2 to the, 2 to the 50th, 1 minus 2 to the 50th, 1. So here's how we can use spectral theory and the notion of diagonalizability to compute a priori very complicated or very tedious expressions, right? So that kind of wraps up the introduction to and kind of first applications of spectral theory. And so from here, we're going to, we'll talk a little bit more about spectral theory, but what we're going to do from here is jump to the abstract algebra of vector spaces.